that. And when they are done, I'm going to put up the data that shows what you answered and what you got wrong. And you just have to look for your iClicker number ID to find where your answer is. I don't put it up by names because I don't want people to know whose is whose. And I just can't email everyone separately. So also, in case for some reason some of your answers weren't going through, you can see if you were doing it wrong. But that's why you did the hard copy. And in the future, make sure you put your last name and you spell it and you put it in some way where I can read it, because my least favorite thing about teaching is alphabetizing. And if you make it harder for me to alphabetize, I'm going to grade harder because I'm not happy. So write your name where I can read it and put your last name, because I alphabetize by last name. So I appreciate if you do that for me, because I really hate to alphabetize. It takes me like 30 minutes to alphabetize for this class. Make it easier for me. So going on with chapter 2, we were starting to talk about some laws, and we're going to continue that discussion with the law of definite proportions. So what was observed and through experimentation and came about by a law by Krauss, and he was a scientist through 1826, is that all samples of a given compound, regardless of where their source is and how they were prepared, they'll have the same proportions of their constituent elements. So what does that mean? Let's look at an example of that to really understand that law. So if we are looking at sodium chloride, if we have 100 grams of sodium chloride, and we have 39.3 grams of sodium and 60.7 grams of chlorine, if we compare our mass of chlorine to our mass of sodium, we have 1.54. Now, if we have a 200 gram sample, the amount of sodium and the amount of chlorine, when we look at that ratio, is still going to be 1.54. And why is that? Well, we know now that's because sodium chloride has the same formula no matter how much of it we have or where it comes from. So the ratio of sodium to chloride is always going to be the same, because the amount of sodium and chloride in a molecule is always the same. But at the time, didn't really know that, and we'll get into that. So that's where that law comes from. So it doesn't matter how much of a sample we have, the ratio of the elements in that sample are always going to be the same. And that'll be useful for us when we're looking at things like elemental analysis to determine what our molecules are made of. So we'll actually utilize this law later on. And another example, again talking about sodium chloride, if we have a smaller sample, again our ratio is always going to be 1.541, assuming we always have a pure sample of sodium chloride, no matter the amount. So that's our law of definite proportions. An example of that, let's say we have 2 samples of carbon dioxide, and they decompose our constituent elements so we can measure how much of each we have. So one sample produces 25.6 grams of oxygen and 9.60 grams of carbon. The other produces 21.6 grams of oxygen and 8.10 grams of carbon. If we want to show that this is in agreement with the law of definite proportions, all we have to show is that the ratio of oxygen to carbon in each samples are the same. That's all we're looking at. So that's all we're showing to show that the law exists. So all we have to do is take our mass of oxygen and our mass of carbon in sample 1 and show what their proportion is. In this case, it's 2.67. And if we look at sample 2, its proportion is also 2.67. So that is in agreement with our law of definite proportions. This is really useful if we have an unknown sample or we want to determine something, because we know that if we have a pure sample of a compound, that their atoms will always be in the same proportion no matter how much of that sample we have. So we're going to actually use that in a calculation. So here's another example, and this is what I was alluding to. Let's say we have a 10 gram sample of calcite. You don't know what calcite is. You don't need to know what calcite is at this point. And it contains 4 grams of calcium. We want to know how much calcite we need to have 0.24 grams of calcium. And we don't know what else is in calcite. Well, you don't. I might, but we don't even know the full formula. But what we do know is no matter the amount of calcite, we're always going to have the same proportion of calcium in it because it's a pure substance. It's a pure compound. So what we're given is our grams of calcite and our total grams in sample 1. Now we know in sample 2, we have 0.24 grams, so we want to know how much calcite that'll be. So our conceptual plan is we know that our ratio of calcium to calcite in sample 1, we're going to call this 1, is equal to our calcium to calcite in sample 2. Because that ratio is always going to be the same if calcite is a pure compound. And I'm just putting a 1 and a 2, meaning sample 1 and sample 2, not Ca2. That's just to make it clear. So since we have that relationship, all we have to do is solve for the amount of calcite in sample 2. So what I'm going to do is figure out my ratio in sample 1. Now you can make sample 1 and sample 2 equal and solve, but just to be clear, I'm just going to solve for sample 1 first. So our ratio of sample 1 is 4 grams, and these are both in grams. We don't have to do any conversions. Of course, if they weren't in the same units, we would. So our ratio there is 0.40. Now notice my grams canceled out because this is a ratio. It doesn't have a unit. And of course, that should be in 2 significant figures. So to figure out what I'm looking for, which is this, I'm going to call it x. I can say what did I press? Sorry about that. Just going to delete that. So, sorry, technology. Sometimes it gives us problems. So we know that this ratio is equal to our calcium in sample 2. And we were looking for our calcite of sample 2. So we're given our sample 2 calcium. It's this. And we're looking for our calcite. So our mass of that. So we can just solve. Remember, we're solving a fraction. And if you need to review some math, you can come talk to me. I can't really go into how to solve this equation. But what we can do is multiply just going to put my 1 in parentheses. We know 0.24 grams times 1 is 0.24 grams. But so when you're following it later, you see that I did that. Then we can divide both sides by our 0.4 to solve for our x. When we do that, we retain our grams because, again, 0.4 doesn't have any units. And we get 0.60 grams calcite. And, of course, this is in two significant pictures. Because this is 2, this is 2. We can double check that by just plugging it in. We already know our ratio of our first sample for 10-gram sample with 4 grams of calcium is equal to 0.4. So to check that, we can just see if we divide 0.24 by our found amount. That should be equal to our 0.4 because that's what our law says, that our proportions will be the same. And if you calculate that, you'll see that it is the same. So it's an easy way to check our answer with that one. So since we know what our proportions are of one sample, we can calculate how much we have of our total sample by doing this. And we'll be doing this throughout the semester with different examples. The biggest one is going to be when we're going to be looking at combustion analysis, which we do often as chemists if we're trying to figure out what amount of carbons and oxygens are in a molecule using this law. Even though we won't always say we're using this law is what brings about our theory that this could work. So we'll be following it. The last law that we're going to be looking at today is the law of multiple proportions. Now this is a little bit different than definite proportions, and I have to say probably one of the laws that's a little bit harder to kind of wrap your brain around what it's saying. But we're going to learn throughout this semester why this law works. So what this says is if we have two elements, let's say A and B, and they have two different or multiple ways where they can form a compound. For example, carbon and oxygen can come together to form CO, carbon monoxide, or CO2, carbon dioxide. So we have two elements that can form multiple compounds. The masses of B that combine with 1 gram of A can be expressed as a ratio of small numbers. Now what's key is we keep A at 1 gram. We could also say that the masses of A that combine with 1 gram of B would also have a ratio of whole small numbers. What does this mean? This is a little bit confusing to think about. So again, carbon oxides can form either carbon dioxide or carbon monoxide. They can come together and form two different compounds. So if we have a sample of carbon monoxide that has 1.33 grams of oxygen for every 1 gram of carbon, and we have a sample of carbon dioxide that has 2.67 grams of oxygen for every 1 gram of carbon, if we take the ratio of 1.33 grams of oxygen to 2.67 grams of oxygen for carbon dioxide, we're going to get a small whole number. And that small whole number is going to be 2 in this case. Because in carbon dioxide, for every 1 carbon we have 1 oxygen, for every 1 carbon we have 2 oxygens, and carbon monoxide, for every 1 carbon we have 1 oxygen. So if we take the ratio of those masses, it's going to be equal to 2 because carbon monoxide has 1 while carbon dioxide has 2. This works, we'll learn, because oxygen has a certain amount of electrons in its outer shell, which dictates its ability to bond and its bonding patterns. Carbon has a certain amount of electrons in an outer shell, so that dictates its bonding patterns. So because we have very inherent things about the molecules that dictate bonding patterns, that's why we have these types of ways they can bond. So basically what this is saying is we have a ratio. And oxygen can bond, if we're comparing these two, carbon monoxide is 1 oxygen, carbon dioxide is 2 for every 1 carbon. Now we want to keep our carbon ratio to 1 because otherwise it's not comparable. So we can't compare the mass of oxygen for 2 grams of carbon and compare that with the mass of oxygen with 1 gram of carbon and carbon dioxide. We have to keep something similar, which is carbon. If we did the same thing and we figured out the mass of carbon and carbon monoxide for 1 gram of oxygen and the mass of carbon and carbon dioxide for 1 gram of oxygen, we'd also get a small number ratio. What would it be? 1, because we have 1 carbon in each of those molecules. So we'd see that. So that's true, and that's, again, it's based on our bonding patterns, which we will learn about later, about how these bond. At this point, we're going through laws, and notice, if this law was by John Dalton, he is the one who proposed it, and he passed away in 1844, this has been around longer than when we fully understood the atom. So the big thing to remember is the law is based on observations of nature. Remember we talked about that. So because of that, they didn't really know why this was always an agreement. They just saw that every time they did this, it worked. And we're going to talk about why this is an agreement later on. So how can we utilize this? Let's look at an example. In this one, we want to show that 2 oxides of nitrogen are consistent with our law of multiple proportions in nitrogen dioxide versus dinitrogen monoxide. And don't worry, later on we're going to learn naming of these things, but it's pretty straightforward. So here we're given how many grams of oxygen for every 1 gram of nitrogen. So what we're showing is that we have this proportion. So what we want to show that this law is correct is see if comparing these two gives us a whole number, small whole number ratio. So all we have to do is take our grams of oxygen and nitrogen dioxide and figure out our ratio to that of our grams of oxygen and nitrogen monoxide. But the key is our nitrogen has to each be 1 gram. If they're not, we'd have to divide it by however much nitrogen we have. But they're both compared to 1 gram, so we're good. So we can take that 2.28 grams in our nitrogen dioxide per 1 gram of nitrogen, and our mass of oxygen and dinitrogen monoxide per 1 gram of nitrogen, which is 0.570 grams, and we see that comes out to 4, and that's a whole number, so that's in agreement with our ratio. So that's just showing that that law is consistent, or that this experimental determination is consistent. Here's another example. Again, you don't really know what hematite is. You could look it up. That's not really a common name that we'll really memorize what that molecule looks like, but it's not necessary for this discussion. So hematite and litharge are just 2 common names for iron-containing compounds that contain iron and oxygen, and we're not really going to get into what that looks like right now. But we have 2.327 grams of iron for every 1 gram of oxygen and hematite, and in litharge, it was found that we had 3.490 grams of iron for every gram of oxygen. So again, we're showing that this is consistent with our law of multiple proportions. So we're going to do the same thing, which is we're just going to show that our ratio of those two are going to give us a small whole number ratio. So we're going to take our mass of our iron in litharge, and it's just because we have more, so we'll put our higher mass at the top, and our mass of iron in hematite. So this is a ratio. We are going to cancel out our units. Of course, these will have to be in the same units for us to be able to do this calculation. So actually, when we do this, if you put it in your calculator, you'll see that you'll get 1.5. So you might say, okay, this isn't consistent. 1.5 is not a small whole number ratio. But remember, 1.5 is just this divided by this, which means for every one of these, we have 1.5 iron elements. Well, we can't have 1.5 iron elements. So, let's say we multiply that by 2. And we'll get a 3-to-2 ratio, which means for every 2 iron atoms in hematite, we have 3 iron atoms in litharge. So that is a small ratio. It's just it came out to decimal place. So the example that we showed before was not a 3-to-2 ratio. It was a nice 4-to-1 ratio. But this is still consistent, even though it's not, even though it's a 3, I don't know where my numbers went, to 2 ratio. So I gave you this one last time, but I'll give it again, because now we've talked about it. Let it do its thing. Well, now you know the answer. Answer it anyway. You get an extra one. So, here what we're comparing as we're going through this answer, which law this is in agreement with. So we have 2 samples of carbon of 2 molecules, pure samples of molecules. So we're going to assume, we don't know what it is exactly, but we're going to assume that they're the same 2 different samples of a pure substance, the same pure substance. So if we compare the ratio of oxygen to carbon in this one, we'll see it's the same number as comparing the ratio of oxygen to carbon in this sample, which is in agreement with our law of definite proportions. So I know you might get confused between the law of definite proportions and the law of multiple proportions. But remember, definite proportions, we're comparing 2 masses of the same sample, saying that every atom, the atoms when compared to each other in a pure sample are going to have the same ratio, no matter how much mass you have. So that's definite. With our multiple proportions, we're saying if we have 2 atoms that can bond in multiple ways, then we can figure out a whole number ratio to compare them to. And that's what we're looking at. So we're looking at multiple ways of bonding and the law of multiple proportions. And of course, the law of conservation of mass is saying if 2 atoms come together to form a molecule, however much mass we had of those 2 atoms, that's how much mass we're going to have of the whole molecule. Now let's get into, again, all of these laws were proposed based on experimental observations way back before we really had the instrumentation we have now to really know what's going on. So for a lot of this chapter, we're going to be looking at how our understanding, as we know it now, of the atom came about. So Dalton proposed a theory of matter based on having ultimate individual particles to explain these 3 laws we just talked about. He said for these 3 laws to be right, each element is composed of tiny indestructible particles called atoms. Just because he came up with it doesn't mean this is all true. This is just based on what he knew at the time. Remember that. Also, he said all atoms of a given element must have the same mass and other properties that distinguish them from atoms of other elements. The mass thing we're going to learn isn't quite right. But some of this is going to be right, meaning there's distinguishing things about the atoms. Also, we'll learn atoms combine in simple whole number ratios to form molecules of compounds. And that he really got from that law of multiple proportions. And we'll see that that's pretty much true. Though 1 and 2, not so much. Why are you going backwards? And then he proposed in a chemical reaction, atoms of one element cannot change into atoms of another element. In other words, you can't combine 2 elements and make gold, which is something that was they were trying to do for a long time. Because gold is an element. So he said from those laws that they can rearrange the way they're attached, but we can't change what one element is to another element. not necessarily everything in this is going to be true. And one of the main things we're going to be focusing on this chapter is number 1, which is each element is composed of tiny indestructible particles called atoms. So before we get into that, we're going to talk about some experimental things that they did to understand what the atom is composed of. But to understand that, we have to talk about some notes on charge. Now, when we're talking about charge, we're talking about electronic charge, electricity, things like that. So when we're discussing this, I want you always to think about a magnet. Because we'll see that our charged particles are like magnets, and that's how they behave. So there's 2 kinds of charges, positive and negative charge. And just like a magnet, opposite charges attract. The positive end of the magnet, the positive pole, is going to be attracted to the negative pole. So if your magnet's turned that way, that's how it'll attract. If you put a strong enough magnet on a table and they're not facing each other, it'll turn to where the attractive forces will come together. But like charges repel. So the positive end of the magnet is going to repel the positive end of another magnet. And if you try to push them together, depending on how strong the magnet is, you won't be able to. So we're going to be thinking about this magnet on a small scale, but you can always think about a handheld magnet. Everyone in here has played around with a magnet at some point in physical sciences, and we're going to be utilizing that concept. And to understand some of the experiments we're going to talk about, we're going to have to remember these notes on charges. Also, remember to be neutral, overall neutral. If something contains charged things, if overall it's read as neutral, we have to have an equal amount of positive and negative charge. And that's going to be important as well to our discussion of experiments and when we start actually talking about what our elements are made out of. So the discovery of the electron was one of the first things that brought about us really understanding what our elements are made up of, what they look like. So further study revealed that an atom is composed of smaller particles than just the atom. And one of those studies came about by looking at a cathode ray. So they have these things called cathode rays. They're produced when high electrical voltage is applied between 2 electrodes in a partially evacuated glass tube. And evacuated just means we're removing the air. And when connected to a high voltage power supply, you had a glowing area seen emitting from the cathode. And you might think about that as, or a lot of study has been on things like cathode rays and lasers. So high density energy. But they didn't really understand what the cathode ray was. They just knew they could make it if they did this. So we wanted to understand what the cathode ray was made up of. So this particular scientist, Thomson, believed that cathode ray was made of little bitty particles with some sort of charge, because it came about when we put high voltage. And we knew a little bit about electricity and its charge. So he wanted to designate an experiment to determine the particles, their charge, and the amount of charge. So he's basically trying to measure the charge. So what he did was, we have some nice sound. So our cathode ray should go in a straight line. That's what was found. So he said, well, let me apply a power supply where I have one end that's positive and one end that's negative, and I'm going to see, is my cathode ray going to go in the same line and hit the target, or is it going to change its direction? So that's what he did. He found that with no power supply in the middle of the cathode ray, it just went straight. But if he applied a positive and a negative end, what he saw was the cathode ray always went towards the positive end. What does that tell us? It must be made up of negative. Because again, that positive and negative attract each other. So it seems like a simple experiment, but this really allowed them to understand, okay, this cathode ray is made up of these tiny particles that are negative. So his results said that the beam always deflected to the positive plate, so it must be made of tiny negative charged particles. And he was able to relate the amount of deflection based on the charge and mass of these particles, and that's something that in chemistry we utilize a lot, especially in something called mass spectroscopy, which we look at the mass-charge ratio when we bombard our molecules with a lot of energy. And if you've ever watched a crime show, they talk about mass spectroscopy all the time. We use it all the time, utilizing this concept. So he also found that, and he was able to calculate the amount of charge in this particle based on that. And he also found that every material tested contained these same particles, which is key. So he tested this with a lot of different materials, and he always found it always went towards the positive end. And then he also found that the mass ratio of these particles was this number, you don't have to memorize it, negative 1.76 times 10 to the 8 coulombs per gram. That's the C. And it was known that the charge mass ratio of hydrogen ion is positive 9.58 times 10 to the 4 coulombs per gram. And again, you don't have to memorize this. This is just a comparison. I won't have you memorizing these things. So his conclusions was that the particle has the same amount of charge as a hydrogen atom. So if it does, then it must have a mass of almost 2,000 times smaller than a hydrogen atom. So we must have things, and remember, hydrogen's our smallest atom. So that tells us we must have things that are smaller than hydrogen. That's what it's telling us. So apparently, based on this, the atom is not unbreakable, because if it was, we wouldn't have particles that are much smaller than it. That's what that really told us. So that means Dalton's theory, at least number one, is not quite correct. So he believed that these particles were the ultimate building blocks of matter. Again, this is based on what he knew at the time. And these cathode ray particles became known as electrons. And we know electrons now, and of course most of you in here have at least taken a little bit of physical sciences, so we're really just going with how these were come about, how we understood them. Now to further understand what was going on, Milken, another scientist, decided to do an oil drop experiment, and this is another one because he wanted to know how big these things were. He wanted to put some sort of size to them. So this is another one where we have to consider charge. What we had was, he wanted to know the charge of a single electron, just one of them, because remember the cathode ray is a bunch of them. But it's really small. So what he did was he took oil spayed in fine droplets from an atomizer, shown in the little corner, and allowed it to fall through a really small hole. And he was looking at it through a light source so he could see it. During the fall, the drops are going to acquire electrons produced when the air was bombarded with ionizing energy, so radiation, so a light source. Radiation just means a form of light. Not necessarily visible light, but just a form of light. And he has a negatively charged plate here. So, if our electrons are negative, they're going to be suspended because they're going to repel from the negatively charged plate. It's basically the concept. And our oil was also repelling each other because if each electron is negative, they're going to repel each other, so the oil droplets are going to repel each other. So therefore, he could, based on varying the amount of charge in the plate, he could slow the fall of the drops, reverse them, or stop them. And then he could actually calculate based on how much charge he was using on the plate, how much charge each electron was having. That's kind of a... And again, remember, this was before we had computers, clearly before we had computers. And it's really sometimes hard to even think about how they designed these experiments when we have so much tools today that allow us to see things. So it's really amazing. And he was able to calculate the mass of the drops and calculate the charge of each drop. So what he found was that drop was always a multiple of a whole number, but a multiple of negative 1.60 times 10 to the 19. And he found that the mass of the electron was in fact 2,000 times lighter than hydrogen. And again, you don't have to memorize these numbers. This is just his finding. So he was able to find our charge. So a summary of electrons. Electrons, as of what we know now, are particles found in all atoms. Cathode rays are our stream of electrons. And the electron has a charge of negative 1.60 times 10 to the 19 coulombs. That's the C. And our electron mass is 9.1 times 10 to the negative 28 grams. Again, this is times when scientific notation is super important. Because you don't want to write these numbers out. So now that's going to bring us to fully trying to understand the atom. This should be a pretty easy one to answer. Remember, this shows the time you have left. Give you a little bit more time because I did that. Sorry. So let's look at the theory of the atom as we know it today. So now they know the atom is not indivisible. There's electrons. So Thomson must propose a new model of the atom. At this point, remember, the rest of the theory is still valid as far as Dalton's theory. So he proposed that instead of being a hard, marble-like, unbreakable sphere, the way that Dalton was describing it based on what he knew at the time, that he actually believed there's an inner structure of the thing, and that there's negatively charged particles, and atoms are charged neutral. So we know atoms are charged neutral. That was something that they had already found. So that means that, again, if atoms are charged neutral, then we must have an equal amount of positively charged something in the atom. And it also makes sense we have to have a positively charged something because electrons are going to repel each other. So how are they staying together? We have to have also a force that's attracting them to keep them in our atom. So he defined the atom as looking like this thing, and he called it a plum pudding model, which I don't really know what plum pudding is, but apparently it looks like this. So that's why it's called that. And he said that the electrons are held together by the attraction for a positively charged electric field within the atom somewhere. And then there's a bunch of negatively charged electrons surrounding it. There has to be a source of positive charge because the atom is overall neutral. But he didn't assume there are any positively charged pieces because it never showed up in the cathode ray experiment. Nothing ever went towards the negative charge split. So he said, well, there can't be a positive particle. We know that's not true. But that was his theory based on what he had found from his experimentation. So he said the mass of the atom is due to the mass of the electrons within it, which we'll learn. No, that's not true. But that's what his theory was. So of course that's incorrect. We know that now. Also, he said electrons are the only particles in his atom, and we also know that to be incorrect. But he was right on some things. That the atom is mostly empty space. He was correct on that. And that negatively charged particles can't be too near each other because they repel each other. So he's also correct on that. He wasn't correct on everything, but he was correct on some of it. Now, to talk about how it was determined that we actually had a nucleus, and that it wasn't just electrons in empty space, we have to first understand a little bit about radioactivity. Radioactivity is mostly, I think, in chapter 19, so we won't be covering it in a lot of detail, but just enough for us to understand the next experiment we're going to talk about. So in the 1800s, Becquerel and Marie Curie discovered that certain elements would emit small energetic particles and rays, and these particles could penetrate matter, and that's the important thing of the next part of the experiment we're going to talk about. So it was discovered that there's 3 different kinds of emissions, and you really can get into that in chapter 19, and if you're interested, you can read ahead, but I won't really be testing you on this. It's just to understand the experiment that we're talking about today. So alpha particles have a mass that's 4 times hydrogen atoms, and they actually have a 2+ charge. Then there's beta particles with a mass of 1 divided by 2,000 hydrogen atoms and a negative charge. And then gamma rays, which are energy rays, not particles, and they don't have a measurable charge. But the big thing is that these things could penetrate matter. And this discovery allowed scientists to experimentally probe the structure of the atom. So it's pretty interesting. And if you are interested in a nice, fun book to read, or listen to on audiobooks, there's a book that's called Radium Girls, all about ladies that used to paint clocks with radium to make them glow. And it's really interesting. They don't get into as much of the science as I'd like, but they really, it's a pretty long book, but eventually get into how it was discovered, what these radioactive materials did to the body based on these women and exhuming their bodies and studying it. So it's really interesting. I would recommend it. It's fairly long, though, and it's written oddly in some parts, like the wording, but it's interesting. Anyway, it's a lot to do with that. But our purpose of this slide is to understand the next experiment, which is these things can penetrate particles. So how can you prove something's empty space? Well, you could throw something through it, fire something through it, and that's the basis of this next experiment. So if we have large target atoms, a very thin sheet of target, so it won't absorb the bullet, and then we'll use very small particles as a bullet with very high energy, so we're going to use some of those radioactive particles. But not so small that electrons will affect it, because we wanted to see if there's anything else in the atom besides the electrons. So we don't want the electrons to be affecting it. So the bullet in this experiment is going to be alpha particles, and our target atom is going to be gold foil. So we wanted to hit the gold foil. We know gold has a mass of 197 atomic mass units. We'll be talking about that later in the chapter. And it's very malleable, which means it's easy to form into thin sheets. It's easy to mold it, which is why we have gold in so many things like jewelry. It's fairly soft. It's easy to make it look the way we want. So it was easy to make thin sheets with it. Not supposed to start there. Okay, so basically what was done, we have gold foil, we have a box that has a radioactive sample, and we're shooting it through the gold foil. And it's going to go through unless if something stops it. And we have a measurement radius, and we're going to measure the angle that the radioactive particles changed when it went through by having some sort of detector in this fluorescence. Fairly simple. So, if it passed straight through, it didn't hit anything, it's going to go straight through. We won't have any change in the angle of the ray. But what was found was sometimes it would be, the angle would change, which means it's not going straight through. And we have some empty space. And they were able to do this a couple of times and see how it would change. And that is just our alpha particles, which we're measuring on the screen. So what Rutherford's experiment showed, the results, was that 98% of the alpha particles went straight through. So whatever is in there, it's small. That's one thing that was found. So most of the atom is empty space. But about 2% of the alpha particles went through, but were deflected by large angles. And a very, very small amount didn't go through, bounced off the gold foil. So that's kind of crazy to think about, considering that's like taking a cannon shell and trying to put it through a piece of tissue paper, because that's how strong these particles were, this radioactive material they were shooting through it, and it bounced back. So they're like not expecting that at all. So that was an interesting thing. It's a very small amount that did it, but they weren't expecting it. So the big thing to remember is that our alpha particles are positive charge. That's the big thing with this experiment. So what does that tell us? That tells us that whatever that thing is that it hit and it deflected, it must also be positive because it's deflecting it. Because if it was negative, it would just be attracting. Also, it must be big enough to interact with the particle. Because remember, our electrons are negative, but it's not interacting with them. So it must be bigger than our electrons. So his conclusions, the atom's still mostly empty space because most of the particles, 98%, went straight through. But it must contain a dense particle that was small compared to the atom's size, but large in mass because it was large enough to interact with our alpha particle. Because of the few that bounced back. And also, it must be positive because we're getting that deflection. So that, of course, is coming to our nucleus. What does that look like? But that's how it was found. Because, of course, we can't see this. We can't put this under a microscope and see it. So in the plum pudding model, this would make sense. All 100% of our alpha rays would go through. But if we had something like what we know today to be our nuclear atom, most of them are still going to go through. But when we get close to that positively charged nucleus, it's going to deflect. If we actually hit it, it's not going to go through at all. And it's going to be bounced back to us, actually. And that's what was found by this experiment. And it's a very useful finding, and that's how we know our atom model to be the nuclear atom, where we have a nucleus surrounded by electrons. So what we know based on this model is the atom contains a tiny dense center, and we call that a nucleus. It's very small space, but it's very dense. So analogy of the size of the nucleus compared to the amount of space the electrons take up is if you had a football arena, say the Superdome, and you had a little pea, a little green pea in the middle of the 50-yard line, the rest of the Superdome would be where your electrons are. And your nucleus would be that little bitty pea. So that is the difference. But the entire mass is in that nucleus. So it's really, really dense. And it has to have been for our alpha particles to interact with it. And we actually know that our electron mass doesn't contribute to our mass of our atom. We also know the nucleus is positively charged because it balances the negative charge of the electrons. So however many, if we have a neutral atom, whatever charge total of our electrons, that's how much positive charge we have to have in our nucleus. And of course, we'll be utilizing that when we actually start looking at the atoms and talking about how many electrons, protons we have. And of course, the electrons are dispersed in empty space. And now we call that our electron cloud. But this is all based on experimentation. So here, based on this model, what we know is that it's false to say that the negative charge is in the nucleus. So that's false. But the other two are true. And still today, that's how we look at our model of our atom. So for the next 5 minutes, we're going to talk about our atom as we know it today. It's cold up here. You'd think me walking around I wouldn't be as cold, but I'm freezing. Technically, I won't really be testing you too much on these experiments. Maybe a little bit. So maybe I could skip them and just give you the information, and we'd get further in the semester. But I think as scientists, it's really more knowledgeable to understand why we know what we know today, and to understand the type of experiments that were done to make us understand what we take as really fact today. We say it's fact. So I think it's really important as scientists we see where it comes from. And my goal in this class is to have you understand what I'm teaching and not just memorize a bunch of equations whatnot. That way, no matter which chemistry class you take later on, you won't have to go, oh, I don't remember that from general chemistry. Because if you understand it, you'll remember it. So that's my goal and why I spent so much time with those. So now we're going to talk about the actual structure of the atom. So we know we have the same amount of positive, guys, I'm not done, don't talk. If I'm talking, thank you, I appreciate it. I know I talk loud, but we want to make sure everyone can hear me. So based on the measurements of nuclear charge of the atom, we know we have the same amount of charge of the positive charge as the electrons. So our charged particles that are positive charge are our protons, and they must have the same charge, equal but opposite as our electrons, which is each proton has a charge of positive 1.60 times 10 to the 19 coulombs. Now we just say each proton is +1, each electron is -1. But this is the actual measurement, and they're equal but opposite. However, our mass is 1.67262 times 10 to the 24 grams. You don't have to memorize that. If I want you to calculate it, I'll give it to you. So since our protons and electrons have the same amount of charge, atoms that are neutral must have the same number of electrons and protons. And we know that to be true when we have neutral elements. So if we know the number of electrons, we can easily know the number of protons, and vice versa. Now let's talk about relative mass and charge. It's going to be really confusing to always talk about mass and charge in these numbers, so we're going to make it easier by basically making it more relevant, dividing by 1 so we can at least have a 1 to something ratio. So when we're talking about charge, it's going to be a 1-to-1 ratio. So we're going to say protons have a +1 charge and electrons have a -1 charge. But again, that's relative on a scale to make it easier for us to understand it and discuss it. And we're going to do the same thing with mass. So we generally talk about the size charge on atoms by comparing the charge on electrons as -1 charge units. So therefore, a proton has a +1 charge unit, or Cu. But often we won't even associate the units with it. It's just understood. And as far as the mass of the atoms, carbon is very abundant, so we do a lot with carbon. So the mass of the atoms was comparing to 1/12 the mass of a carbon atom that has 6 protons and 6 electrons. So we call that 1 AMU, or 1 atomic mass unit. So I mentioned atomic mass units a couple of slides ago. That's where that comes from. So because we're talking about 1/12 and we have 6 protons and 6 electrons, protons have a mass of 1 AMU. Electrons have a mass of 0.00055 AMU. But that's so small, we consider it irrelevant, so we don't consider it. Clearly it has a mass, it's a thing. But it's such a small mass, it's going to not change the total mass of our compound. So we just consider ourselves with the mass of the protons and not mass of electrons, since they're so small. Though, they're really important because they contribute to charge. So let's say we have lithium. Lithium has 3 protons. Now they're near each other in the nucleus, shouldn't they be repelling each other? Also, we know the mass of lithium to be 6.941. Which doesn't make sense because we only have 3 protons. So there must be something else, some other particle present in the nucleus that's able to separate the protons enough where they're not repelling each other and also contribute to the mass. So what does that come from? And that's what we're going to call our neutrons, our neutral. So that's our last particle that's in our atom that we'll talk about is our neutron. It's about the same mass as a proton, slightly heavier, but relatively we'll say if a proton's 1 AMU, a neutron's 1 AMU. Again, being relative. But it has no charge. So this is just that in summary. And on Monday, we're going to delve into this more, actually look at how this contributes to our atoms. Have a good weekend. I have pushed back homework too because we're clearly not done. Okay,